In the Wawa Mountains of western Utah, there is a mine that produced one of the rarest gemstones on Earth for about 15 years and then stopped. Not because the deposit ran out, because the price of what it produced dropped to a point where the operation cost more to run than it earned. The mine sits at about 8,000 feet elevation in a range that most people drive past on the way to somewhere else. It produced red beryl, a mineral so uncommon that geologists estimate roughly one specimen exists for every 150,000 gem-quality diamonds ever found. When the price structure changed and the mining company walked away, the deposit did not disappear. The geology that produced it is still there, the crystals still forming, still sitting in the rhyolite matrix where they grew, unreachable without significant equipment and investment that at current prices, nobody has decided to provide. The assumption most people carry about gems is that diamond is the standard of rarity, that the scale goes from common rocks at one end up through semi-precious stones to sapphires and rubies and eventually to the rarest thing, which is diamond. The assumption is wrong, and it is wrong in a specific way that says more about marketing than it does about geology. Diamonds are found on every continent except Europe. They have been located in Russia, Canada, South Africa, Australia, Brazil, Botswana, Angola, and in deposits scattered across Central and Western Africa. The largest diamond mining operations in the world move millions of carats per year through a supply chain that has been deliberately managed since the 1880s to prevent the price from reflecting the actual volume of supply. De Beers, the company that built the modern diamond market, spent most of the 20th century controlling roughly 80% of global rough diamond supply and releasing product into the market at a rate calibrated to maintain prices. The rarity of diamonds is a managed rarity, a commercial position held in place by supply control and by one of the most successful marketing campaigns in the history of consumer goods. The phrase, "a diamond is forever," was invented by an advertising agency in 1947 and is now so embedded in cultural practice that most people experience it as ancient tradition. Painite sat in museum collections for decades before anyone understood what it was. The mineral was first described in 1957 from a single specimen found in Myanmar, named after the British gemologist Arthur C.D. Payne, who brought it to scientific attention. For the next several decades, fewer than 10 specimens were known to exist worldwide. As recently as 2001, the Guinness World Records listed painite as the world's rarest mineral. Then miners in the Mogok region of Myanmar found additional deposits, and several hundred specimens eventually emerged. The supply remains tiny by any commercial standard. Faceted painite stones of even 1 carat appear at auction rarely and sell for prices per carat that exceed most colored diamonds. The mines that produce painite are not large operations. They are small workings in an area of Myanmar where artisanal mining has been ongoing for centuries, where rubies and sapphires and spinels come out of the same alluvial gravel deposits, where a person sifting material by hand might find a painite crystal and might not know what they have until someone with a refractometer tells them. Alexandrite was discovered in Russia's Ural Mountains in 1830 in an emerald mine near the town of Yekaterinburg, and the initial specimens were reportedly found on the birthday of Tsar Alexander II, which is how the mineral got its name. The original Russian deposits were largely worked out by the early 20th century. What makes alexandrite unusual is not just its scarcity, it is the only gemstone with a color change strong enough to be reliably visible under normal lighting conditions. In daylight or fluorescent light, alexandrite appears green, sometimes a strong bluish green. Under incandescent light, the same stone appears red or purplish red. The shift is caused by the way the chromium atoms in the crystal absorb different wavelengths under different light sources. Fine alexandrites in the original Russian deposits changes color completely and shows strong, saturated color on both sides of the shift. These stones sell for prices per carat that routinely exceed those of comparable quality rubies and sapphires. Brazilian alexandrite was found in the 1980s and has become the primary commercial source, but the color change in most Brazilian material is less pronounced than in the best Russian stones. Sri Lanka, Tanzania, and Madagascar also produce alexandrite, none of it in quantities that approach common gem production. The mines that produced the original Russian alexandrite were emerald mines that discovered something unexpected. When the emeralds gave out and the economics changed, the mines closed. The alexandrite that remained in the ground in the portions of the deposit that were not fully worked stayed there. Grandidierite was first described in 1902 from a specimen collected in southern Madagascar and named after Alfred Grandidier, a French explorer who spent years documenting the natural history of the island. For most of the 20th century, clean, transparent specimens were essentially unknown. Opaque material existed in small quantities, but nothing suitable for cutting into a faceted gemstone. In 2014 and 2015, transparent grandidierite began appearing on the gem market from a deposit in southern Madagascar that had been found by local miners. The supply was not large. Within a few years, the accessible material had been largely extracted and gem-quality grandidierite became difficult to obtain again. The stones that entered the market during that window are now in private collections and occasionally appear at auction. The deposit that produced them was not a formal mine. It was an artisanal operation, local miners working a specific location with hand tools and selling what they found to dealers who traveled to the area. The buyers were gemologists and dealers who had been following the Malagasy gem market long enough to recognize what was appearing. Most of the grandidierite that came out of that deposit went to buyers in the United States, Europe, and Japan within months of being excavated. Benitoite is the state gemstone of California, which is a distinction with an asterisk. The only confirmed gem-quality deposit of benitoite on Earth is the Benitoite Gem Mine in San Benito County, California, which gave the mineral its name when the crystals were first described in 1907. The mine has gone through multiple ownership changes, periods of active production, and periods of closure. It was worked commercially until the 1990s. Since then, it has operated primarily as a fee dig site, where visitors pay to search the tailings and the accessible areas of the deposit for crystals. The commercial operation concluded that the remaining material was not worth extracting at scale. The fee dig operation continues because people will pay for the experience of finding a crystal in the original deposit, and because occasional good specimens still come out. Benitoite fluoresces bright blue under short-wave ultraviolet light, which makes it visually spectacular in ways that photographs cannot fully capture. The crystals are typically small, triangular in form, and often associated with white naturalite that sets off the blue color. Fine faceted benitoite stones of 2 carats or larger are genuinely rare, not in the managed sense that diamonds are rare, but in the straightforward sense that the supply is a single location in one city of one state, and the accessible material is largely extracted. The question of what gets left in an abandoned mine is partly economic and partly practical. Mining operations close when the math stops working, when the ore grade drops below what the processing operation can handle profitably, when commodity prices shift, when equipment needs replacement that costs more than projected revenue, when a company runs out of capital, when an owner dies and heirs decide not to continue. None of these closures necessarily mean that the deposit is exhausted. They mean that the deposit is no longer economical for the operation that was working it at the scale it was working at with the technology it had available. What a large commercial operation finds unworkable may still contain significant material that a smaller, more patient operation with lower overhead could extract at a profit. This is why abandoned mines attract the attention of artisanal prospectors, mineral collectors, and small-scale gem dealers who work deposits that larger operations have walked away from. The economics are different for someone with a pick and a sorting table and no corporate overhead than they are for a mining company with equipment, staff, insurance, environmental compliance costs, and investors expecting quarterly returns. Musgravite was first described in 1967 from specimens found in the Musgrave Ranges of South Australia. For decades, it was known only from a handful of specimens, and confusion with the closely related mineral taphite meant that some specimens were misidentified. By 2005, fewer than a dozen faceted musgravite stones were confirmed to exist. Additional deposits have been found in Antarctica, Madagascar, Greenland, Tanzania, and Sri Lanka, but none of them have produced significant quantities of gem-quality material. The stones that do appear on the market come from small pockets in these deposits, found occasionally by miners working for other targets, recognized by someone familiar enough with the material to know what they are looking at. Taphite itself is worth addressing because its discovery story is one of the stranger ones in mineralogy. The first described specimen was a faceted gemstone that had been sold as a spinel. The Irish gemologist Richard Taffé purchased it in a lot of spinels in Dublin in 1945 and noticed that its optical properties were different from spinel. He sent it to the Natural History Museum in London, where it was identified as a new mineral. The only reason it was discovered when it was, rather than decades later, is that one trained observer bought a lot of stones from a dealer and noticed something was different. Mines that produced taphite did so without knowing it, because the specimens were being misidentified and moved into collections as something else. The geography of rare gem deposits has an interesting pattern. Many of them cluster in specific geological environments: pegmatites in Brazil, East Africa, and Madagascar, metamorphic belts in Myanmar, Sri Lanka, and Tanzania, rhyolite-hosted deposits in the western United States, ancient cratons in Australia and Russia. This clustering reflects the specific geological conditions that produce these minerals. Certain gems require element combinations and pressure-temperature histories that simply do not occur in most places on Earth. Alexandrite requires aluminum, beryllium, and chromium to occur together in the right proportions under the right conditions. Benitoite requires barium, titanium, and silicon in a chemical environment that has only been found in a fault zone in a specific part of California. When a deposit with those conditions closes and walks away, the minerals it produced do not form somewhere else. The specific location that has the specific geology is the only place those crystals exist. This is qualitatively different from diamonds, which form under conditions that are common enough across the deep earth that new deposits are still being found regularly. The economics of rare gem mining are unlike the economics of diamond mining in ways that have practical consequences for what happens to abandoned deposits. Diamond mines are large capital-intensive operations run by major corporations with the infrastructure to maintain extraction over decades. When a diamond mine closes, it usually closes because the economically recoverable reserves have been genuinely worked out. Rare gem deposits are typically smaller, less homogeneous, and less predictable. A pocket of fine alexandrite, or red beryl, may be concentrated in an area of a few square meters within a broader deposit that contains far less material. The economics of extracting that pocket depends on finding it, and finding it depends on working through material that may produce nothing for significant stretches of time. Large mining operations optimize for consistent grade and volume. Inconsistent pockets of exceptional material in a matrix of ordinary rock are exactly the kind of deposit that a large operation is poorly structured to work efficiently, and that a small operation can sometimes work profitably precisely because the overhead is low enough that intermittent finds justify the effort. The tailings from old mines, the waste rock, and processed material piled outside the workings sometimes contain gem material that was not recognized or not recoverable by the original operation. Processing techniques and identification knowledge have both improved substantially since many of these mines were active. Material that was discarded because the equipment of the time could not sort it or because the operators did not know what they were looking at may contain specimens that are now recognizable and valuable. Fee dig operations at sites like the Bonitolite Gem Mine in California and various locations in North Carolina, Virginia, and Montana work partly on this principle. The tailings at previous operations considered waste still produce specimens because the original processing was not optimized to capture everything. A visitor spending a day sorting through material has access to the accumulated rejects of previous operations, some of which contain things those operations missed. The rarer a gemstone, the more specific and harder to replicate the geological conditions that produced it, the more the existing supply is genuinely finite. This is not a commercial position, it is a physical one. Red beryl from the Wawa Mountains exists because that specific combination of rhyolite chemistry, hydrothermal activity, and element availability occurred in that specific location at a specific time in geological history. The conditions are not occurring in other places in the same way. The deposit that the mine walked away from contains what it contains, and when that is extracted, there is no equivalent source waiting to replace it. This is what distinguishes genuine geological rarity from managed commercial rarity. Diamonds are managed. Painite is not. Bonitoite is not. The abandoned mine in the Wawa Mountains is not closed because red beryl ran out. It is closed because the economics of extraction at scale did not work at current prices. The crystals are still there. The geology is still there. What changes over time is not the deposit, it is the economic context around it, the price that fine red beryl commands, the cost of extraction at the elevation and location of that mine, the availability of investment willing to accept the risk. When those numbers change, someone will go back. Until they do, the deposit sits at 8,000 feet in a mountain range most people drive past, unreachable, unchanged, and full of something that exists nowhere else on Earth in comparable quality.